Hey guys, how you doing this lovely afternoon? This is Mr. Maestas here with you, and we're looking at lesson 6-1, which is the second fundamental theorem of calculus. It's fun, it's demental, it's fundamental. And then we're going to look at my second video. We'll look at interpreting rate graphs and how we would interpret that in context, because there will be context on, especially on the free response version, part of the AP exam. So let's take a look, guys. We're looking at the second fundamental theorem of calculus. So I want you to recall that if we take the derivative of an integral, oops, ouch, I just banged my knee. If we take the derivative of an integral, we're just going to get what we have inside, right? It's kind of like they cancel each other out. So let's just take a look at establishing this here. I'm going to take the antiderivative of this, and that's going to give me t squared minus 3t. I'm going to go ahead and evaluate that from 0 to x, and I'm just going to plug in the x, right? It's going to be x squared minus 3x. If I plugged in the 0, I'll just end up having 0. So this is going to be my answer for that. So now, let's say I have this part right here, right? And I take the derivative of what I had before. So the derivative of this, right, the derivative of that is going to be 2x minus 3. Well, look at that. See, all I did was plug in x into this t, and I ended up with 2x minus 3. That's interesting. So what does that tell me? Well, let's see what I'm doing. If I take the integral of a derivative, then I'm going to take the antiderivative at x, because I'm going to end up plugging the x in, right, minus the antiderivative, and I'm going to plug in this second one here. That one I had 0. This one I would have 10. Now, if I take the derivative of that, what's the this part right here? This is constant. And what's the derivative of a constant? It's going to be 0. So really, the derivative of an antiderivative from a constant to x is just going to be f prime of x. So it's just going to be whatever I have in the inside, just plug in an x. That is the second fundamental theorem of calculus. All right, so all we're going to do is plug in x in there for t, and we get our answer. So let's take a look at a different, whoa, got an itch in my back, a different situation here. Let's suppose it doesn't go to an x, but maybe something like an x squared. So what I would do here is I would have f, I know this is going to be f of t, evaluated from 0 to x squared. That's going to give me f of x squared minus f of 0. So now let's take the derivative of that, because I'm taking the derivative of this integral that I had here. And the derivative, so what's the derivative of f of x squared? Well, that's going to be f prime of x squared, but I have a chain rule. I have to deal with the derivative inside. So that's times 2x. And then, of course, this here is constant. So I'm going to end up with just f prime of x times 2x. So that's interesting. I had to deal with the derivative of this limit here and put it kind of like almost like a hook, right? Let's take a look at this one here. So this is going to be f of t evaluated from x cubed to 2x. So I'm going to have f of 2x minus f of x cubed, right? And if I take the derivative of that, which is what 8 is asking me to do, the derivative is going to be f prime of 2x times the derivative inside, chain rule, which is 2, minus f prime of x cubed times the derivative inside, which is 3x squared. So it looks like what we're going to have to do is plug in this 2x into here, and then on top of that, put a little hook value, because we're dealing with a chain rule, of the derivative of whatever that is, right? The derivative of 2x is 2. And that is essentially the second fundamental theorem of calculus with the chain rule attached to it. So if we have anything u and v that are not constants, they're functions of x, we're simply going to plug those in right here, okay? And then we're going to attach a derivative to it. Let's take a look at a few examples here. All right, so Ooh, let's change the color. Let's change it to green. Okay, so this one here, we have a derivative. Now notice we're going from x to a constant. Now really would like that to be a constant to x. So we're going to go constant to x, constant to x. Now anytime we flip the integration, anytime we flip the limits of integration, we have to make this negative because it's kind of like we're changing the area. You know, we're looking at the top area instead of the bottom area. Okay, so now we're going to end up with negative 2x plus 3. And that's all there is to that one. And what about this one? Now this is a constant to a constant. So a constant to a constant is just going to end up being the derivative of a constant to a constant is just going to end up being 0. Because we're going to end up with the derivative of this, and we're going to end and put those in, and we're just going to end up with 0. Okay? We really have to have a x value, an x or a function on there for us to even have anything other than 0. Okay? So let's take a look at the next one. So this is a situation here. We have a constant to an x cubed. So anytime there's something other than an x, we're going to need to do the little chain rule issue. So what we're going to do is we're going to plug in x cubed for my t, and then we're going to attach the derivative of that. Now the derivative of a constant is just 0, so then this is all we're going to have. I'm going to simplify this just a little bit to x to the 6th plus 2x cubed. Okay, I'm going to leave it like that. Let's take a look at 12. So again, we have 2 of them now that we have to deal with. So we're going to plug this in here. We're going to have 3x squared plus 2 times 3x. And we're going to multiply all of that by the derivative of 3x, which is 3, plus, minus. Then we're going to plug in 2x times the derivative of that 2x, which is 2. Okay? I'm going to go and leave it like this. If you wanted to, you could simplify it if you want, but we're just going to go and leave it like that for now. Just to give you the idea of what we're doing with the second fundamental theorem of calculus. Okay, ooh, this is g of x and f of x. This is not actually an x squared or x cubed. So what are we going to do? We're going to plug in g of x. So 2 times g of x minus 3 times, what's the derivative of g of x? G prime of x. Minus, we're going to plug in f of x. And what's the derivative of f of x? F prime of x. There you go. That's it. That's all there is to that one. All right. Seems a little confusing, but it's really not. All you got to do is remember, take derivatives, and attach them on. Put some hooks. Now this one just looks different because instead of saying d dx, I'm saying that f is equal to this integral function and find the derivative. But basically, we're doing the exact same thing. It's just worded a different way. So we're going to plug in 3x squared and multiply it by the derivative, which is 6x. And we have a 0 here, so that's just going to give me 0. So this is just going to be our answer here. Let's go ahead and simplify that a little bit. 9x to the 4th raised to the 10th times 6x. And that's it. That's all there is to that one, guys. All right, so there you go. That's the second fundamental, whoa, all over the place. That's the second fundamental theorem of calculus, both the regular version and the chain rule version. We'll catch you soon. Bye.